Happy Friday, podcast listeners. Welcome to another great episode of Podcast with Gautam and Jin. Thank you for joining us today. My name is Jin Vanstee, and with me is my co-host, Gautam Siwach. Today, we're excited to have Thomas Harrer with us. Thomas is an IBM Distinguished Engineer and CTO of Server and Storage in Europe, Middle East, and Africa. Thomas's expertise is in hybrid cloud and AI platform, infrastructure for mission-critical applications, and cyber resiliency. Thomas, welcome to our podcast.
Thank you very much, Jin. Thank you for having me, and also hello, Gautam.
Now, Thomas, let's start with cryptography. Why is cryptography so important for our economy and for our life?
Actually, the world depends on data and on private exchange of data, of security, of secrets. So if we unleash every secret, the world would not work as it is. And we rely on cryptography to make sure that these secrets kept secret. When we, for example, communicate on the internet, we are using crypto protocols like TLS in our browsers. We use VPNs, virtual private networks, which are actually all based on encryption. And large corporations actually use encryption to secure their most critical data. Then in case if that data gets stolen, hackers, evil organizations could abuse that, could earn some money out of the data, but they can even get insights into that organization that they must not have. So the whole world, the economy actually, all the contracts that we are doing, the trust that is there is depending on strong cryptography. And we are lucky we have that cryptography for many years. In certain flavors, we have the symmetrical crypto algorithms like AES, American Encryption Standard, and based on long crypto keys like 256 bits, it's considered quite secure to encrypt all the data using these algorithms. But there is also the class of asymmetrical crypto algorithms like RSA, so Reverse Chauvet Edelman, or Diffie-Hellman, and these kind of asymmetrical schemas are used to do some advanced crypto protocols like key exchange, like digital signatures to assure that things are real and the ownership rights are there. So that is the reason why I would say our world really depends on these strong cryptographic schemas. And actually today it works quite well.
So is this existing cryptography still secure enough for all time in the future?
Yeah, and here the issue really comes in. So RSA was considered to be very secure because it used a one-way function, so to say. The function is calculating the prime factors of a large integer number, which is very difficult if the number is given and you need to find the prime factors. If that number is very large, it takes millions of years to calculate on classical computers. The other direction to calculate the product of two prime numbers is very easy. So in one direction it's easy, in the other direction it's very hard for classical computers. Or the discrete logarithm that is used in the Diffie-Hellman key exchange. Also one direction easy, the other direction very hard. Same is with elliptic curve algorithms. And exactly these principles are behind all the existing or the well-used asymmetrical crypto schemes that, let's say, make the signatures, the key exchange really valid. Now we know since the middle of the 90s that there is an attack to these algorithms, which is the Peter Shor's factorization algorithm. Peter Shor developed an algorithm intended for running on quantum computers based on some mathematical principles of quantum Fourier transformation. But at the end, if there would be a large enough stable fault-tolerant quantum computer available, many of these hard problems become easy to solve, or probably instead of millions of years, they could be solved in a couple of minutes. And this is the reason why we expect that many of the today's established crypto algorithms, especially the asymmetrical ones like RSA, like Diffie-Hellman, in the way they are today, will not continue to be secure. And actually, this is already a problem today, because if there is some data encrypted based on keys that have been exchanged by Diffie-Hellman today, and if that data is captured and stored for later reuse, if that is harvested in 10 years from now, for example, it still contains some secrets about organizations, about people, about money, about things that should not be known. And especially when it comes to military information, that is going to be very severe. So organizations need to think about what will happen if these existing encrypted data is stored and then decrypted in 10 years or even in 5 years if the development is going to be faster.
Now, how to mitigate these severe risks from eventually broken crypto protocols?
Yeah, and the very good thing is that there are quantum safe crypto algorithms already available. They have been developed since many years because the problem is not new. And this year, in July 2022, there has been a milestone reached, which was the announcement of the first 4 candidates for standardization. The National Institute of Standards and Technology, the NIST, has established a standardization process for post-quantum cryptography or quantum-safe cryptography already in 2016. And many organizations have worked on algorithms that are likely to be too hard for a quantum computer to be cracked. And a class of these algorithms is called Lattice Encryption algorithms. Many of the, or actually 4 have been selected for standardization, and 3 of them have been heavily shaped by IBM research, by IBM colleagues in research, mainly in Zurich, Richelieu-Con. And this is for encapsulation mechanisms, the crystals Kyber algorithm, which is a lattice-based one. And for signatures, we have even 2. We have the crystals dilithium and we have Falcon. Why we need 2 or even more? Because of performance characteristics. Not every algorithm is fast enough to accompany any kind of application. So for certain applications with requirements of very lean algorithms, we need something different. And Falcon, also lattice-based, is a little bit leaner than the lithium. The 4th algorithm that has been named candidate for the standard is Sphinx Plus. It's a hash-based algorithm. Actually, IBM has not co-developed it, but one of the co-developers now works for IBM. And so we can say IBM, the IBM company, has expertise because we created the algorithms that are very, very likely to be the next standards. There will be more standards, of course, and standards will change, but these algorithms go into something that already can be trusted. And we invest into putting these algorithms into our key offerings and products. And the most important product to mention here is the IBM C or Z system. With the IBM C16, which we have announced this year in April, it is the first system in the market that can be called a quantum safe system, because already in the startup phase, all the microcode, the firmware is secured by post-quantum, quantum safe cryptography, and the system has accelerators on board like the Crypto Express 8S card that implements Kyber and dilithium, so both flavors of quantum safe algorithms that are going to be standardized by the NIST. And therefore, customers with very sensitive data in the military area, in public, but also in banking, in insurance, wherever very sensitive data is processed, they can start securing the data right now to avoid the growing risk of data that is harvested today and then exposed in the future. So IBM probably is a great partner for companies to establish a strategy towards quantum safe, which probably starts with knowing the data. So something called a discover and classify process, then a crypto inventory is important to become at the end crypto agile, which means that it should become easy to replace existing crypto algorithms for the data that deserves it with more modern, more stable, more impactful algorithms without too much work. And when companies are crypto agile, they probably will be able to implement crypto safe, quantum safe algorithms easily and adopt if we will see that some of these existing quantum safe algorithms come out to be not as safe as we think, because mathematics will never stop in its development, and you never know what will be possible in the future. And it could also be that a traditional algorithm comes up where the hard problems of today are solvable easily in the future. And then organizations really need to act quickly and have an agile way to replace existing cryptography with the more stable quantum or other safe cryptography.
In addition to safety, quantum does offers a chance to address world-class challenges which are unsolved. Today, our speaker Thomas Harrer discussed about the importance of security while working with data in general and during our conversations over networks. Please feel free to reach out to him if you have ideas or concerns around safeguarding your information or enterprise data. You're listening to podcasts with Gautam Siwach and Vanstee. Thank you for supporting. Please share and continue listening.